So in order to test methods that we write for binary search trees, we might want to be able to walk through the tree and print out everything that's in it. There are a lot of different ways we can walk through a tree, but the one we're going to talk about here is called inorder. And it's nice because for a binary search tree, it will print out everything in the tree, as the name implies, in order, from least to greatest. The basic idea is that we process the left child, and then the parent, and then the right child. And this will be a process that will work somewhat recursively. We'll basically run the same process on each of the subtrees that are rooted at the left child or the right child. So here's how we'll start. We look at the root, that's 100, and we go to the left, right? Because we go to the left first. And now we're looking at 50. We say, okay, can we go left from here? And we can. So we're at 200, at 20. We can go left from there. So now we're looking at 10. And now we go left from there again, and now we're looking at 5, right? And 5 has no left child, so we don't have anything to do for left. So then we look at parent, right? That's 5 itself. So we'll write down 5. And then we look to see if it has a right child, and it doesn't. So we're done. So now we've finished the left bit for 10. So we do this parent bit. So the next thing in our list is 10. And then we look to see if it has a right child, and it does. It has 15. 15 doesn't have a left child, so we don't need to do anything there. Then we process 15, and then it doesn't have a right child, so we're done there as well. And we come back up to 10, and we're done. So from 10 we come back up. For 20 we've handled everything to its left. So we process 20 itself, and now we consider what happens when we go to the right. We look at 30. We look at its left child. It's 25. It has no left children. Then we process 25. It also has no right children, so we're done. Let's mark the ones we've done. We did 5, then 10, then 15, then 20, and now 25. And we come back up and process 30 itself before looking for its right child, right, which is 40. 40 has no left child, so we process 40 itself. Has no right child, so we're done. We come back up, then go back up to 50. Everything to its left is done now, so we process 50 itself. Go to the right from there, right, and following the same process we get 80. Now we've made it back up to the root, to 100. We've done everything to its left, so we process 100 itself. And now we can look to the right. We can go to 120. We can't go to the left, so we do 120 itself, and then we go to the right. We're at 130. We can go to the left from there to get 125, and then back up to 130, and we're done. Right, so this is the idea. We always do everything to the left, then back to where we started, and then everything to the right. And that's how we end up with this list from least to greatest. Because if we go as far to the left as possible, we get the smallest thing. And the thing as far to the right as possible will be the largest thing. So if you look at the code that's shared for binary search trees, it's recursive, and what it basically does is it calls that same function itself on the left child, prints something for the root and then calls it for the right child.